I would like to get into this workshop, this course, like step by step. You see, we have so many things to see in these 3 days, and also I will be preparing another part, another small part here at the end because I didn't have the time to do this. Um, so mainly we will be working with Millipede and Caramba 3D. But also, of course, as we are going to discuss some optimization and structural optimization, we are going to also rely on Kangaroo for a small part of the course. And as I told you, it's better to have a comprehensive setup of plugins because you never know what component you might want to use in your definition. So many times happens that a plugin has some utility that becomes very useful in a workflow that doesn't include the plugin itself. Okay, so that's why I recommended to install most of the plugins that you see in my recommended list. So I hope you had no problem with this because eventually we are going to use some of those components. But mainly we are going to focus on Kangaroo, on Millipede, and on Caramba 3D. So as you might know, also Millipede is basically, it has been discontinued. I really don't know why, because it was a very nice software and a very useful software as well. Actually, if you want to have an alternative to Millipede that is not Caramba 3D, as you know, Caramba 3D is a commercial product, so you might run into licensing issues. Unfortunately, I didn't receive the license from the guys at Caramba 3D for this workshop. Maybe they forgot. Luis Antonio, I have problem installing Caramba. Okay, let me finish, and then eventually we are not going to use Caramba 3D now at the beginning. So eventually during the break, or soon after or before the break, we are going to see what happens with your Caramba installation. Okay. There is also another alternative you're welcome. Another alternative to Millipede that is not Caramba, and it's called Topos. It's here. It's this small T here. It's basically it's very similar to Millipede. The only thing that you must know if you want to use Topos is that it runs on GPU. So you must have you should have a GPU capable of running this software. It's somehow tricky to set up the GPU behavior in Topos, but once you do it, you can simply run the software. It's quite fast, and it's also more powerful, a little more powerful than Millipede, because it allows to work with any basically solid shape. I don't know if you have already run some tests with Millipede, but Millipede is somehow stuck to working with boxes. Okay, so we will be discussing this later on, where we will be dealing with 3D topological optimization. But we are going to start with Millipede as regards frame analysis and optimization. So it's going to be somehow easier as a start. And then there is Caramba 3D, of course. Caramba 3D is, I would say, it's one piece of a software because it's so powerful, so complete, and it can do so many things. And also, somehow it tends to be like more professional. I would rely on the results from Caramba 3D in a more professional way, of course. But nevertheless, sometimes using like other software like Millipede, for example, or even Kangaroo, it's very useful to have an idea on how the structure is going to behave in real life, even if you don't have the exact calculation of stresses and reactions and deformations and so on. Okay, but in order to have an idea of what is going to happen in your structure, maybe Kangaroo is already reliable enough, to have a general idea of the behavior. And the other thing that we are going to use quite a lot is optimization processes. Um, Now, in Grasshopper, as you might know, there is already an optimization tool which is called Galapagos, which is this one. It's called Evolutionary Solver. Actually, all of these tools that we are going to see, like Galapagos, Opossum, I think I will talk about this, but maybe I will not be using it. And Goldfish, of course. Um, they basically work the same. The only difference between, for example, Galapagos, opossum, the main difference, not the only difference, but the main difference between Galapagos and opossum goldfish, which can be like, let's say, put together in one different, in one special category, is that Galapagos can only optimize one parameter at a time, while opossum and goldfish, they can work with a multi-objective optimization. So you can decide, for example, how many parameters you want to optimize in your workflow, and then these two software here can give you an optimization depending on many features of your model, not only just one like a Galapagos. So I'm going to start with this. So just to give you an idea of on how these tools work. There is a question. Okay, perfect, Ariel. Nice to know this. Okay, so just to have an idea on what are these three software here, even if they work differently, I'm going to show you Galapagos just because we are not going to use it. So you also know if you need to run a small optimization in any of your definition, you can rely on Galapagos if you don't want to use these two tools here. So Galapagos is somehow a strange component in Grasshopper. It's and also opossum and goldfish would work the same. So we are already introducing some features from these optimization tools here. It works differently from standard Grasshopper components because you don't plug things into Galapagos. You plug things from Galapagos. Okay, so you drag wires from Galapagos to other components. Okay, so for example, just so that you see how this component works, I'm going to create some very stupid things. So I'm going to create in Rhino a circle like by, let's say I want to create it by area, okay? So, or by circumference. So basically, if I am now at more or less 15, I see 15 meters is the circumference of this circle. Okay, so keep this in mind. So I'm going to set the circumference of this circle to 20. Okay, so I know this circle has a length of 20 meters. Okay, so here in Grasshopper, I'm going to create a circle whose center point is going to be at the center of the existing circle. Okay, so I'm going to create this circle right here. What I want to do, I want to ask Grasshopper, I want to tell Grasshopper, I need the length of this circle. So the circumference of this circle to measure exactly 20. Okay, so in order to do this, what I implement here in Grasshopper is a workflow where the radius is my variable. Okay, so the radius can be whatever. You see that in this case we have a radius of 1, while in order to have a circumference of 20, we must have a radius of more or less 3 units. Okay, so I would use here a radius between 1.00, let's say 000. I will also tell you why in a minute, and 10. Okay, so we have a variable radius for this circle. If you change this, eventually you will get to the exact value of the radius of this circle. That corresponds to a length of the curve corresponding to 20 meters. Okay, why did I use so many decimal numbers? Because if I don't do this, I will have either a smaller circle or a bigger circle. So if I want to optimize things and in order to get to a very specific value, it's better if you use many decimal numbers here. Okay, so now everything is ready. What I need to tell Galapagos is that the genome which are the parameters for my small optimization workflow, are the variables. So it's going to be this slider here. And the fitness is the value that I want to optimize. Now, if I analyze the length of this curve, I will get some value here. It is actually more or less 13. So what I want to do, I want to take this value here. I put it into a number container. This is not necessary, but for clarity, I do prefer to keep things, let's say, very organized in my definition in order to avoid wasting time understanding what I was doing just 5 minutes ago. So the fitness is going to be this thing here. So I drag a wire from fitness to the number container. Okay. So now Galapagos knows that it must change this slider here in order to optimize this value here. Okay. Now everything is set in my small definition here. So we can keep things under control by putting this circle here on the left and double clicking here in the Galapagos component. So this is Galapagos interface. So what I want to do with this interface is basically define what are the criteria for my optimization process. So what I want to do here is, first of all, as regard the fitness, do I want to maximize or minimize the result? So this number. In this case, I don't want to optimize in these terms. Normally, you can use Galapagos, for example, to determine what's the smallest area under certain circumstances. Okay, so this is when you use minimize or maximize. But if you want, you can also place here a value. So you want the fitness to be 20 because this was the value that we wanted to get. Okay, so then you switch to solvers, which this is the part where Galapagos like calculates the results. And I do recommend that you, if you are not running very complex simulations, I do recommend that you display all genomes in the Rhino viewport, which means that each variation that you have in your slider will be affecting the preview in Rhino. If you have a very heavy definition and a very large amount of geometry, you might want to avoid this because refreshing the viewport and the preview is something that it's time-consuming for the computer, so you might have less resources for the Galapagos evolutionary calculation. Okay, so I do recommend in this case it's just a small circle. So display all genomes in the Rhino viewport. And then you decide what type of solver you want to use. Galapagos only allows to use one, which is called the evolutionary solver, and one is called the annealing solver. Talking about solvers, I would not go too deep inside this thing because then there are opossum and goldfish, which are more complex. But if you want to know more about these solvers, algorithm, and processes, you might do a Google research. There is a lot of material in order to understand how they work, but it's a very, let's say, in-depth look to this kind of software. Okay, so unless you are not a mathematician or something like that, it's something that you might not want to further investigate, unless you want to get scared somehow. But anyway, I would rely on the evolutionary solver, then you start the solver. So you see that now Galapagos, what it's doing is changing the value of this slider randomly. So this is like somehow a brute force attack. Okay, so Galapagos is changing this value, and it's seeing what's the result, how this change affects the fitness value. And once it starts detecting that some values are determining a result which is closer to the fitness value, then it takes those values and concentrates on them. So you see that the curve starts to reach the top of this graph here. So it means that the radius, as you can see here, the circumference, sorry, tends to be 20. So it's like, it's not an intelligent approach somehow. So it's like stochastic, you know, it's random. At the beginning, you have a very huge variation for these values here, but then Galapagos concentrates only on the values that are producing the best fitness value. And then it starts to dance around those values until it gets to the well, I would say the perfect result, more or less. If you see this thing here, for example, it's reaching 20 point something, something, something 7. You know, it's very, very small difference between this and the fitness value. It is possible that by having defined only 6 decimal values here, it is not possible for Galapagos to get to exactly 20. So this is a problem in Grasshopper and in computational design in general. In order to be extremely precise, you need also to have a huge amount of decimal values. So it is not always convenient to do something like that. And also there is a limitation here as regards the number of decimal values that you can use in a slider. So in this case, eventually Galapagos will not get to 20.0. Okay, but anyway, this is precise enough to us. So the best result is actually this one. It's on top of this list. When you see this, you might want to wait for Galapagos to reach the maximum amount of iterations that you have defined here, or the maximum amount of time if you defined it. But if you see this, you can stop the solver, and then you can reinstate any of these values here. And of course, we are going to reinstate this one, which is the perfect value to us. So reinstate. And now we know that the radius of our circle is this one here. Okay, so the optimization process is somehow it's not so smart actually. So it's like banging the head on a wall until you get the desired result. Okay, so this is my definition of evolutionary solver with Galapagos. Okay, but nevertheless, it's absolutely useful when you have some problems that you need to find the solution, but you don't want to find it yourself. You just let the computer run its simulation until it finds the result, and then you can go out and have your life, and then go back and see what's the result. Okay, so if we delete the rhino circle, you'll see that grasshopper circle is actually coincident with the rhino. So this is how a solver, an optimization software works. Okay, and goldfish and opossum works the same, but they allow a multi-objective optimization. So you see that the limitation with Galapagos is that it only allows one fitness value. You cannot optimize several fitness values. So it's just one number. Okay, so you cannot optimize several variables or fitnesses at once. Okay. Eventually, if you want to work with Galapagos and not with this more complex software, you must find a way to let's say, include in one single value all the parameters that you want to optimize in your workflow, in your definition. Okay, but this is something that we're not going to discuss because we are going to switch to goldfish eventually. Okay, so this is how Galapagos works. I'm going to leave this here, just like a introduction to evolution to optimization software, and let's jump into the architectural things. I'm sure, and this is somehow important, I'm sure that you already know something about Kangaroo. We are not going to discuss Kangaroo. If you need to refresh something about Kangaroo, even if we are discussing something like architectural structures, it is enough to eventually watch the 2 free sessions that I have on my YouTube channel on elastic simulation, elastic systems with Kangaroo, because actually it is enough to simulate catenary structures. Okay, so I'm not going to discuss Kangaroo today in details. I will only use it to create some catenary structure in order to run some optimization processes later. Okay, so I prefer to concentrate a little on the other 2 plugins, which are Millipede and Caramba 3D. So let's start with Millipede, and let's see what Millipede can do actually. So I have prepared well, quite a bunch of scenarios here. I'm going to turn them on one by one, so you will see what's the behavior of this plugin. This is a very simple structure, 2 columns, 1 beam. Millipede actually, in this case, is just running a simulation. Okay, so Millipede in this case can predict what is going to be the behavior of this structure under certain circumstances, like loads and supports and so on. Okay, so this is a very simple simulation. We can build it from scratch in order to understand what's the workflow. But in terms of structural simulation, all the plugins work basically the same. Okay. Um, I also want to discuss a little thing with you, because this is something new in the Grasshopper world, because a new plugin recently came up, which is called Peregrine. Let me write it down here so you can find it. It's free, so you can install and test it. It's called Peregrine. Um, this is another structural simulation and optimization plugin. Actually, it's very, very interesting. Unfortunately, I couldn't put this plugin in this workshop because it just came out. Basically, it's very new, and also because I myself am attending some webinars with the developer in order to deeply understand how it works. But it's very promising. It's absolutely astonishing as the potential that it has. Actually, it is sponsored by ARUP, so it is used in a production environment. So you might want to double check this plugin. So take a look at it, because it's very promising. It's very useful as well. But they all work the same. So once you know how one plugin works, you know all of them. The only thing is to find the right components, because everyone has its own set of icons and names and so on. But anyway, you define a system, which is basically the geometry of your system. You define loads and supports. And then there is a simulation and somehow the visualization of the results of the simulation. Okay, so they all work like this: 4 steps. You define the system, you define loads and supports. Then you run the simulation, and then you have some tools to make some visualization, like stress visualization, deformation visualization, and so on. Okay, but we are going to discuss this with Millipede and with Caramba 3D. So you see that if you want to see this scheme in action, you see that actually this is the definition of our system. So you see here we are defining both the system and the loads, because Millipede allows to define the load at the system level, at the geometry level. So you see that we are defining here some framing, 2 types of framing. Of course, there are basically these here. You see there is a list. These are 2 lines, so these are the columns. And here there is one single value here. This is the beam. Okay, so you see that for each element you define the geometry, which is this line, and then you define the material, the cross section, and the load. And here you have the single line for the beam, the material, the cross section, and the linear load is actually here connected to the same slider. So it's just to have some load applied to the 2 elements. Okay. We are going to discuss this in detail because there are some tricky aspects. Okay. Then there is the support definition. You see, you decide where you want to place the support and what type of support you want to use. Another type of support, which is the intersection between the beam and the columns. Then there is finally building the model, which is the model, which is basically assembling all the information together in order to create the only FE model. Then there is the simulation. So this is the simulation. Millipede is not famous for its for its graphics. So you see that the icons are quite ugly, but anyway, they are functional. So the FE model is passed to this solver. The solver emits another FE model, but with the analytics of how it works. And then you have some visualization, which is the one that we were seeing with deflection, for example. And also you have an idea of here you see that the solver also emits some information about the weight of the structure and so on. These are information that we are going to use, for example, during the optimization processes. Okay. So I repeat, you have system definition, which is basically geometry and physical properties. Then there is loads and support. And then there is the assembling the model, running the simulation, and visualization of the results. It's always the same. Okay, so no matter what plugin you use, Millipede, Karamba 3D, Peregrine, whatever, you always have this kind of workflow. Now, let's do this from scratch. Okay, so let's see how we can implement this definition and see what are the tips and tricks for this thing. Even if Millipede is discontinued, I encourage you to use this until it becomes not compatible with Grasshopper or Rhino or whatever. Okay, so I have made it available on my cloud hard drive, so you can download it from there. I guess you already did, but it's a very nice plugin, and somehow it allows doing some very interesting optimization analysis. So let's start with something, let's say, normal today. So what I'm going to do, I'm going to define some lines, actually. So I will use, well, no, not like this. I prefer to draw them here in Rhino. So let's use some simple line vertical. Let's rely on the grid. I'm not taking into account actually the size of this geometry here, but one important recommendation. I don't know what unit system you are using in your life. I work with meters. So one recommendation is always start with a new template in meters. Before doing anything that's related to architectural design, even if you are working in Grasshopper, which, as you know, is unitless, some things, even if it's unitless, some things depend exactly on the units that you are using in Rhino document. So for example, when you define a load in Millipede, you are defining the load in Newton per meter. So if your model is not drawn in meters, you will have some scaling factor that will affect the simulation, like no deformation at all, for example, or no stress at all, or exaggerated stresses and deformation. That's because of a scale factor as regards to units. Okay, so just pay attention to this and do it at the very beginning of your workflow. Don't do this later, because some things are not taken into account on the fly from Grasshopper. Okay, so I do recommend that you always start your Rhino template with meters. Even if you are not used to work with meters, some plugins like Millipede and also Karamba, they work with this system. Okay, so you must work with the same units. So we have the file correctly set up in meters. Now I am drawing some lines, and I will draw also a beam here. We can also do something different in order to don't repeat exactly the same thing. And I'm going to connect also this and this. So a very simple structure here. And what I'm going to do in order to keep things organized, I could I can do two different things here. I can import all the lines together into one single component and work with them without separating them by functional elements. But I do prefer to keep things organized and clear in my definition. So in this case, what I'm going to do, I'm going to import the columns, like with a curve component, set multiple curves, and also the beams with another curve component, set multiple curves. So here we are. And as I'm going to share this this file with you later, eventually at the end of this course, I will always be internalizing data in order to have the Grasshopper definition not depending on the Rhino file. So here we don't need the actual geometry. You can delete it. Okay, so we have the columns here, the beams here. I should name them, label them, but anyway, you get the point. Okay. So Millipede, you might have noticed that when you run, what is it? Yeah, it's this. When you run Grasshopper and you have installed Millipede and you start using Millipede, a message pops up that say that this version has expired, but this is just because they didn't develop new versions. So that's why you have this message, but you just ignore it. Click the OK button and then you're ready to go. So in order to understand what you have inside here, Millipede, there are, let's say, several groups. The first one, the eigen, is basically related to vibrational system, more or less. So you might want to perform like eigen analysis if you want to understand what are the vibration or resonances that you have inside the structure. So it's very, very tricky things. The FE system is the one that we are going to use right now. So it's like, it's based on frames. Okay, so this is frame analysis somehow. So it's the simpler one. There are some geometry utilities if you want to just give it a try. They're pretty straightforward. There is a parameterization group of components. The important ones, just to concentrate on the important ones, is the FE system, stock, TopoStruct 2D, and TopoStruct 3D, and also some utilities as all the plugins in Grasshopper have. Okay, so we will be focusing on these four groups: FE system, stock, TopoStruct 2D, and TopoStruct 3D. These allow the topological optimization. That's why they are called topo. Something related to topology, actually. Both in two dimensions and 3 dimensions. We will be discussing this later. This is going to be the last part of the course. But today we are going to concentrate on FE systems. So inside this thing here, we must define FE frame elements. You can define elements, like I was saying, in several ways. If you want to work with the complete set of curves, you can take the frame curves. You just feed all the curves inside this component. And then you define one cross-section, one linear load, one support type for the whole system of curves, okay? But in this case, as I want to analyze things separately, I maintain things separated. And so I prefer to use, you can derive the elements from a mesh, you can do many things, basically. But anyway, we are going to use the FE frame element. And the FE frame element, unfortunately, which is something that actually I would have optimized somehow in the plugin development, but you see that it doesn't accept curves or lines. It asks for initial start point and end point of each element. So what you must do here is take this, calculate the endpoints. So you have the P0 and P1 input and plug them here. Now, one thing, and this is first tricky things in here in Millipede. Even if you know that if you have here like 4 start point and 4 end point, this component should create 4 different connections between the first start point and the first end point and so on. But as here you are blending many information like cross-section, linear load, up vector, it's better to keep things like separated from the procedural point of view. So I do recommend here that you use this little trick will do the work. So you graphed the start and end. So in terms of lists or of data sets, they are absolutely separated from each other. So you will see that here you have one single list of 4 points, and here you have 4 lists, each one containing 1 point. And so you will have basically this component will clearly understand what cross-section to assign to which connection and so on. Okay, so this is a little tricky, both because you have to extract the endpoints and then you have to graph them before connecting them to the FE frame element. But do this because it keeps things clearer and makes this component work properly. Okay. Cross section. Now, the cross-section is something that you find in stock. So you see that there is this cross-section component. One must get used to these kind of icons. At the beginning, they're like, I really didn't like them when I first saw them, because there is this transparent area here. They are so different from everything else in Grasshopper. But anyway, you get used to this. And you see that the cross-section is something that you can customize almost completely. So if you right-click on this icon, you see that there are some presets somehow. Well, basically some templates, I would say, not presets. Actually, this is based on Circle Hollow. But I would say that in this case, eventually, as we are talking about, if I'm not wrong, columns. Yeah, the columns. So let's say we are going to simulate some kind of metal structure. Okay. Or if you want, you can simulate something like 4 concrete columns and then metal beams here on top of them. But it depends on you. Okay, this is possible because we have separated the columns from the beams, so you can define different cross section and different properties. Besides the general aspect, which in this case I would use an I-beam, you see that when you change the template, you have different inputs here, of course. And if you get closer, you would see what A refers to the width of the beam, B the height, and T1, T2 the thickness of the wings of this element, okay, or the body. So when you change these, you will have different inputs. This is something very common also with other plugins like Karamba 3D. When you change template, you will have a reset of the inputs. And so if you had something connected, it will disconnect automatically from the inputs because they have changed. But anyway, an important thing here is the material. So once again, you go into stock, and you have 2 ways of defining material. There is the isotropic material, which is somehow a customized material. If you want to do this, you must provide all these parameters here, which are specific for each type of material. So if you know the well, the modulus of elasticity, the Poisson ratio, density, and yield strength, then you can define whatever material you want, okay? But in general, there is another thing, which is the material, which is another library, if you want to call it like this. You can select between the main materials that you might want to use in your architectural design. For example, if we want to simulate like metal columns, then in this case, we can use, I don't know, high-strength steel or steel. You can change it dynamically once you have defined your workflow. You can also change the material and see how these affect the simulation. And so we plug the material to the math input. Everything is already set. And then we define these values here. Remember that we are working in meters, okay? And so unless it is specified by the parameter here, the input, you must provide quantities in meters. Okay, so for example, you will see that in Karamba, for example, sometimes it asks for a cross-section parameters in centimeters. Okay, pay attention to this because this will affect, of course, the result of your simulation. Now, in this case, A is the width of our cross-section. I would create some square-ish beam or square-ish cross-section in this case. So A and B is going to be the same value for the columns. So I'm going to use something like, I don't know, 0.30 in order to reach up to 1 meter if you want. This is quite a huge structure. We have more or less a 18-meter span in this direction. So it's quite a huge span. So let's give this the proper range. And I'm going to use this as A and B at the same time. So it's going to be a square column, basically. And T1 and T2, I'm also going to use the same value. You can, of course, you can use proper values in case you want to simulate a specific structure. This is just for understanding how these things work, okay? So T1, T2, even if this is going to be like centimeters, remember that you are working in meters. So in this case, I would use something like, let's say, 0.0, I don't know, something 2 centimeters up to let's say 15 centimeters. And so this is going to be T1 and T2. And of course, these values will affect many behaviors, like, for example, torsional behavior and so on. So once you have this, cross-section is properly defined, you can plug this here in cross-section. Columns, linear load. Now, in this case, for example, what we can do, we could take, we could analyze the system like in a very analytical way. We could take, for example, the weight of the beam and split it in order to have the proper weight applied to the top of each column. But anyway, this is something that, of course, you will do if you are defining a real structural element system. Okay, but in this case, I will only concentrate on the behavior. So linear load asks for a vector, of course. It asks for a linear load in Newton per meter. So the vector is going to be actually the orientation of this load. So normally it's going to be a unit C with a factor of -x. So whatever value you plug inside this factor input is going to be negative because of this -x. And this is going to be the linear load. Now, in this case, it's going to be -1 Newton per meter, okay, which is something it's ridiculous. But we can also plug here a slider like an 11 slider, which has a range up to 100. And so plug this here, and we can consider positive loads, but we know that they are going to be applied in a negative direction, so downward. Okay, and up vector. Now, up vector is somehow tricky. The up vector defines the alignment of the cross section. So as regards columns and beams, the cross section will be oriented in two different ways. So you can see, for example, here where I defined the column, which are the vertical elements, the up vector is being used, and it's the x vector. One would expect the z vector because the columns are vertical actually, but no, this defines the orientation of the cross section, not the orientation of the beam or the column. Okay, so in these vertical elements, the cross section is oriented horizontally. So you must provide an horizontal direction. It could also be y, if I don't remember wrong, but keep in mind that it must be perpendicular to the element that you are defining. Okay, so in our case, we are also working with columns. Okay, so they are vertical elements. We need an horizontal orientation to define the alignment of the cross section. And so in this case, I will once again use the X orientation. I didn't try this because normally I use to define a square cross section for the columns, but this would affect, I suppose, the orientation. If you don't have a square cross section, then by using X or Y, you would change the orientation of the cross section. You can try this by yourself. So up vector is going to be this one. So even if it's called up vector, remember that this defines the orientation of the cross section. So it has nothing to do with the up direction. And so the frame element columns are defined. Here they are. If you want to, in this case, if we have grafted these endpoints, so this is receiving 4 different beams, 4 different columns, okay? And they are separated into 4 different lists. What is the use of doing this? The use of doing this is because soon we are going to define different cross-section per element. And in that case, we might want to also graft these values here, okay? Let's do the same for the beams. So the beams, once again, I'm going to do this quicker in order to don't waste too much time. Of course, I could copy paste, but I prefer also to repeat sometimes the process because it helps fixing some concepts. So remember the grafting of these points here. As regards the millipede component is going to be exactly the same. So frame element makes no difference between beams and columns. They can also be, they can also have, it can also receive like connection with some inclination. Okay, so they are always frame element. There is no column or beam. It's just the behavior that defines the beam and the column, not the orientation. So we have the points, start point, and end point. Now, in this case, what I'm going to do is defining the material, the cross section. The material is going to be this. Let's see if this is preserved. So I'm going to take another ID. No, it gets disconnected every time you change this. All the inputs are disconnected. So now I would say that A, which is the width of this beam, is going to be exactly the same the same thickness. Well, sorry, the same width of the column. So I would use this slider here also to define the width of this column of this beam. Sorry. While the height can also be a copy of this slider, and I would say eventually this is going to be 0.50, like 30 by 50 centimeters, the cross section. And also T1, T2, I'm going to use the same technique. Basically, I'm not going to differentiate T1 and T2. You can do this in a real structural simulation, but you get the point. So the cross section is already defined. And linear load, exactly the same. I'm going to copy this, apply to linear load. Then we are going to double check and see what happens with these loads here. And the up vector in this case is 0, 0, 1. So for beams, you can simply avoid defining the up vector because the cross section is oriented vertically. So 0, 0, 1 is actually the z-axis. So it's perfect like this. And so we have the frame element that corresponds to the beams. Next things, we have defined, so in this case, the columns, beams, linear load applied to them. We can also, let's say, define additional loads, of course. So, for example, let's say that I want to simulate, these are the beams, okay? So I'm going to select one single beam, like, what was the first? This one, okay? And I'm going to use a point on curve, leave this to default 0.5, so it's going to give the midpoint of this beam. And I'm going into FE system and define FE point load. Okay, so the application point is going to be this one. And as regards the load, once again, is a vertical vector or a vector that defines the orientation. We can also apply some load with an inclination or a different orientation. But anyway, in this case, we are going to apply a vertical load. So I'm going to copy paste this unit z vector with this factor here and use it like a vertical load. So this is an additional load applied only to this point of this specific beam. And then finally, supports. Now, in this case, what I'm going to do, I'm going to define some fixed support here at the base. And I'm going to define some rotational support here at the connection between the beams and the columns and the joint in this corner here. So as regards the support, there is an FE point supports here that allows to define the supports. And you must provide the point and the support type. The support type is in stock. So it's here. And the points where I want to apply this specific support type are going to be the 4 points at the very base of my structure. We already have these points because they are the start point of the columns. So our columns are here. The start point are these are the columns. The start point are these 4 points here. So I'm going to do something very, let's say, unaesthetic from my point of view, like this cable crossing all the definition. But anyway, you see that Millipede has this kind of straight-ish connection, so it's not that dramatic. Normally, I would prefer to create a wireless container here and then plug it into a point. But anyway, to avoid this kind of spaghetti effect. And the support type is going to be this one. Now, the support type is very simple. The icon represents the type of support. This is a fixed support in this case. It depends on these 6 parameters, so 6 degrees of freedom. You can simply tweak them with a Boolean toggle. So by default, they are true, which it means that the support is basically avoiding the X, Y, and Z translation and the X, Y, and Z rotation. Okay? If you change one of these to false, you are freeing basically the X translation. Okay? So you might want to define this like this. So let's organize this a little better. And then you plug this. You see that when I plug this, the icon changes. So it only constrains the rotation in this case. But if I start also to plug this, you see that it is actually constraining only the Y rotation and the Z rotation. The X rotation has become like solid black, so it is allowed. So if I false everything, you see that this support is basically non-existent. Okay, so let's go back to true for everyone here. Let's go back to a fixed support type. So we are saying that the 4 start point here, the base points, are going to be fixed support. And then I'm going to also define these upper supports. We already have these 4 points. Now we can derive this point as the start endpoint of the beams or endpoints of the columns. It's easier to use the endpoints of the columns because the endpoint of this beam overlaps with, is coincident with the start point of this other beam. So we should separate these points physically because there are 2 coincident points here. But as the endpoint of the columns, they are one single point. So once again, let's take this, let's copy paste it, move it like here. And now let's use the endpoint of our columns. And in this case, what I want is to avoid rotation and allow translations. Okay, so this is what I'm going to do here. So this structure can deform freely because these points are not, let's say, connected to any physical constraint. Okay, they can move because the structure can move, but what they avoid is the relative rotation between the beam and the column, the beam and the beam, and the other beam and the column. So this is a rigid joint, basically, but it can move in space in 3 directions. So I think that's pretty it. We have defined also the additional load here. As regards the loads, you can define loads in different ways. You see that we have defined the loads at the frame element level, but you can also define load regions, for example. You define a boundary in which the load is applied, which is a boundary that can encompass, for example, the whole length of a beam, for example. But anyway, when you define the load, you can also define the load case. So you can define different sets of loads with different values, so different intensities, different orientation, whatever you want, okay? And once you define, for example, load case 1, load case 2, load case 3, you can dynamically change which load case you want to simulate in your system, and then Millipede would give you the result of that particular load case. Okay, but anyway, we are just going to define one single load case, so it's not let's say important to us in this moment. So these are our elements for the system. So now we must go into FE system once again and build the FEA system. So the first step is to merge together all the components or the elements of our system. So we take first frame element, second frame element. Everything goes in the same input. Okay, so elements, loads, supports, everything. So let's plug also the other support, and that's it. These parameters here affect the building or the assembling of the FEA system. For example, merge tolerance. What happens if you have a little separation between the end point of the column and the end point of a beam? So the merge tolerance says that if there is this kind of very small separation, the system must be built as if they were connected in the joint. Okay, so these are basically geometric properties of the system. Okay, once we have this, we can run the simulation. Let's take the FE solver. Let's plug the FE model to the FE model here. Okay, and that's it, because in this case it's extremely fast. We will see later that it can take a very long time to simulate a structure, but in any case, this is actually already outputting an analyzed FE model. You don't see anything because these components, this function here, have no preview. Okay, but if you go into FE system, as the last step, you have these visualization tools here. So frame results, for example, this is an analytical result. These are results from an analytical point of view. So you have force at start point, force at end point, moment, max stress, and stiffness. Right? So if you're willing to get some values from your simulation, you will get them from here. So these that you see in black here, they are basically analytical outputs, extrapolating the analytical outputs from the simulation. And here you have the graphical aspect. So in our case, we're only working with linear elements, so it's useless to visualize stress lines. They are basically non-existing. Mesh visualization, of course, less than stress lines. So the only thing that we can do is to create a frame visualization output. So it asks for the FE model. And you see that here we have the elements visible in 3D. So you can recognize here the cross section. Let me see if I can, yeah, I think it's visible here, the I beam and the I column. Okay, thicknesses and so on, everything is set by these values that we have defined here as the cross-section parameters. There is one thing that's the only thing that I would suggest you double check here. You see that the solver not only gives you the FE model, the analyzed FE model, it also gives you the weight of the structure, which is one important parameter. I do recommend that you start getting used to do this thing here, which is taking a number component and a panel in order to visualize this numerical result, which is somehow extremely important to us, because this is going to be part of the optimization that we will run later. Okay. Eventually, I would take this container here and give this the proper name. Sorry, the proper name. So it's going to be weight. And also, if you want, you can also use the same here in order to give a title to this panel here. Then there is max deflection. So this is another number actually that gives you the max deflection, the maximum deflection that you have inside your structure. So you see that this structure is quite rigid already. Okay, it's not deforming that much. Nevertheless, it's important to understand, in general, it's important to understand what deformation is going to affect this structure. Okay, and in order to do this, you can do this at the level of frame visualization, because you see that there is deflection here. Now, you have a max deflection here, and you have deflection here. You can relate the two things together. So one smart way of doing this is to do something like taking a slider like between 0 and 1, which is a natural slider, and dividing this value by the maximum deflection. Of course, this is going to produce I would say, a very intense effect as the deflection. Okay, this is not the real deformation that you get in your structure, but it gives you an idea of how your structure behaves under these load cases and system definition. So if you start to increase this value, you see that this is the deformation that you tend to get in your structure. Okay, and of course, you might notice that if you go into the front view, if we go into the additional point load that we placed here, and we start to increase, we should see some effect. We don't see any effect actually. Well, this is strange. Maybe due to the fact that the deflection is so small in this case, eventually there is basically almost no difference between these two deformations. Eventually, if we amplify the deformation a little, maybe this is going to change, but I don't think so. But no, it's basically the same actually. But anyway, you get the point. You have an exaggerated deformation by using this method, but this gives you an idea of how your structure behaves under this particular load case. Of course, if you, let's say, put some emphasis on this deformation, this allows to better understand what consequences any tweaking of these parameters has on your system. So for example, if I decide to, let's say, increase the width of these columns and also the beams, for example, by tweaking this value here, if I increase it, you see that we have this change in the geometry, but we also have some differences in the strength of the elements. Okay, so you see that by tweaking the thickness, for example, we have this this change in the deformation. Also, these are the beams. So also for the beams, if we increase the thickness, you see that they tend to bend less. If we decrease the thickness, they bend more. They should also have some torsion somehow, because we have some asymmetrical load in this structure. But anyway, you see that the deformation is affected directly by the height, in this case, of our beams. So you can see basically it's an amplified deformation, of course, remember, but you get the point. You have an idea on how the structure behave according to your let's say parameters here. You can also dynamically change this. This is possible just in this case to perform these dynamic operations, because Millipede is capable of calculating in real time the actualized simulation. Okay, but when you have more complex structures, in that case, maybe it's not healthy to do some real-time variations in your inputs. So in that case, what I do recommend normally is that when you want to tweak parameters in your system, I would suggest you take the solver, Control E the solver, so it doesn't calculate anything. Then you do all the changes that you want, and then you reactivate the solver. Now, in this case, you see it's almost real time, instantaneous, the result. But anyway, I do recommend that you do this without having the solver calculating in real time, because it can be so time consuming that Grasshopper can hang, okay, and eventually crash. So try not to stress the computer if it's not necessary. Okay, and eventually, if you want to do some additional stuff with these results, you have the output of the frame visualization. Remember that this is the deformed version of your system. So you have curves, which are basically the axis of your system. You see that there are linear curve and polyline curve. Now, the linear curves will almost surely will be the columns, and the polyline curve is going to be the beams, because they are not straight. Okay, so if you see that they are somehow alternated here, polyline linear, so they don't preserve the order. So in case you have very complex systems, you must come up with a strategy to isolate the proper elements that you want eventually further investigate or use them for further design processes. I don't know, whatever you have in your mind. In this case, it's very simple. If you see this order, you just dispatch these values. And so we should have, like, let's say, take a curve container. So this is going to be the beams, and this is going to be the columns. Okay, so you see that also the columns, they are deforming a little, because you see that actually the deformed system is compressed, of course. So the columns are shorter. This is the actual intersection of the joint in the system, undeformed system. So there is always some deformation occurring in the two types of elements. Um, and this can give you, for example, something like, in order to also visualize these deformations here, if you have your four beams here, and you have the four original beams here, you can use these two set of lines to create some visual representation of the deformation, not at the mesh level, but for example, if we loft the original curves, like grafting the original curves, like this, and we loft them with the output curves. I hope the order is going to be preserved. They are not blending. This is real life tips and tricks. So you see that we have four curves here, but there is no loft coming up from this operation. This is because this tree has a different structure. So you see that the branches are named 0, 0, 0, 1, 0, 2, 0, 3, while here we have 0, 0, 0, 0, 0, 1, 0, 0. So it's another level inside the tree structure. So in this case, you just simplify the two trees, so they get to the same simple structure, 0, 1, 2, 3, and the curves will finally blend in a single loft. But in this case, you see that they are sorted differently. So I saw it already, because when you have this here, it means that beams and columns are not sorted like in the original system definition. So you must come up with some strategy to properly sort the beams, the deformed beams, according to the same order they have in the undeformed system. So I want to loft the original beam with the deformed one, the original beam with the deformed one, and so on. This is not happening because these beams are sorted in a different way. Okay, so you must, let's say, define a strategy to resort your deformed system in order to correspond to the undeformed system. But this is something that eventually I can leave it to you. You can come up with some strategy in order for this to work properly. So the objective was to have this kind of deformation represented with a surface, a connection surface. You can give colors to the surface, so you have a visual representation of the deformation. I will leave this like, well, actually, I will leave all of this like here, so you can play with it if you want. So this is it. You can see, you can simulate, let's say, very complex structure if you want. So this is a replica of this first small simulation here, and then there is this one here. So let's see how can we perform a frame optimization inside, or well, based on Millipede analysis. Okay, so let's start talking about frame. Well, actually, in this case, it's frame optimization. It can be whatever type of structure, but in this case, it's going to be frame optimization using Millipede. So what I have here, I'm going to show you what's the thing here. It's basically this same structure, but on a multi-story building. Okay, so we have ground floor, first, second, third floor, and this is the roof level. So what I want to do here, I want to optimize or come up with an optimized version of this structure. And you might already notice that this is already optimized, of course, as you can see. There are the thickness or the size of the cross-section of this column is changing progressively from bottom to top. So 0.36 to 0.26. So of course, this is determined by the load that each column must bear at its own level. Okay, and then you can see that also the beams have a different sizes. Now remember, this is somehow like theory, um, because when you run this kind of simulation, you can also come up with a very detailed result. I think it's not healthy to think about creating like uh, four different beams, one measuring 26 by 25, another one exactly the same, and then you have 25 by 27, 25 by 27. Of course, this from the analytical point of view is perfect, okay? But this also means that you must create um, let's say, customized beams at each level of the structure. So it's unhealthy somehow, or anti-economic. So eventually you can base your decisions on this analysis, which means, by the way, that eventually you can use beams like 26 by 27, and you know that this thing is going to work properly. Um, Also remember that we are going to perform some kind of multi-objective optimization. So we are going to use several parameters at the same time to optimize the structure. And we will see what these parameters are. Okay, but anyway, this is already the optimized version of the structure. Oh, one thing that I forgot: even if we don't have the possibility of analyzing stress lines inside our very simple frame, the frame visualization is not only visualizing the mesh. Okay, if you right-click on this, you have several, let's say, visual output. Okay, so if you want to, let's say, visually see the deflection in these elements, even if you have a system which is deforming very little in this moment because we have changed the parameter of the beams. If you change this visualization from none, which is only showing the mesh, to deflection, you see that this thing is actually showing the deflection level, which is higher in the red areas, of course, and lower in the blue areas. So you see that also the columns have some gradient of blue, which means that dark blue is not getting deformed, but at the top they are being deformed, which is compression in this case. In the beams is more evident because this is where you have the highest, the maximum deflection. So you know where the maximum deflection is happening right now. But you can also visualize the stress. So for example, axial stress, of course, the axial stress is more relevant in the columns that are compressed and not in the beams. This is quite obvious. Bending moment is more obvious, for example, that it's affecting the beams at the extremes, where we have the fixed, well, it's not fixed support, but this avoids mutual rotation. So you have moment acting here at the connections. Um, Torsion, you see that in this case, for example, it says, well, actually, this means that it cannot calculate this value. Eventually, as we are working always with loads aligned with the axis, torsions in this case are not being calculated. But normal stress, once again, yield and shear. Deflection, we already know this. Stress, tension, compression. This is something that, for example, it's quite interesting when you are working with truss systems. It's nice to see this diagram here of tension, compression, and stiffness factor, which is something that we are not basically capable of seeing right now. This depends basically also on the material. So remember that everything must be set up properly in our system. But anyway, let's stick to the geometrical aspect in this case. Eventually, we will take a look at stresses in Caramba, and also when we will be performing some topological optimization. Okay, so that's why you see that in this second example here, you see that these beams and columns are getting some color. it is because of the frame visualization. Okay, so this is the bending moment. But also you can switch to any of the parameters that we have seen. Even if you see this red here, actually I had a discussion with a colleague, which said, I don't like the way this color look on this structure, because when you see, every time you see red, it's like an alarm, right? So it tends to be like worrying when you see this kind of red stains in your system. But remember that we are somehow considering the red actually, as we are showing the deflection, the red actually corresponds to the maximum deflection. And the maximum deflection is 0.000291. So this is the red. So when you see red, it's not necessarily bad. So if you are running an optimization, the red will always correspond to the maximum deflection. But if you have optimized the deflection, then it's going to be a very small value. So red doesn't mean bad in an absolute way. Okay. So you see that these are the areas that are being deformed. You see that in this case, for example, there are different levels of red at the same height of this structure. It depends also on the optimization that I have run with goldfish in this case. So let's jump into this definition, because it starts to be more interesting from the optimization point of view. Okay, of course, in terms of elements, it's going to be exactly identical to the previous example. So there is always columns and beams, even if in a multi-story building. But you see that here we have the definition of the columns and beams. Now, the only, and in this case, I'm working with, let's say, concrete beams. So you see concrete columns and concrete beams. The material is visible here with this little white description at the bottom of the material component. So we have square column and rectangular beams. Now, the only thing that I want to point out in this case is that I did some calculation in this case. First of all, let me get rid of the analytical, let's say, representation of this frame system, deformed frame system. You see that here there is some kind of, let's say, labeling going on. This is basically the thicknesses and the width and thicknesses of beams and the structural element that I am using in this system. There is another tag here. So this is just visualization. Okay, this is just labeling the elements. It's not relevant from the simulation point of view, of course. So all that you see here, this thing, you can also disable it totally. It doesn't affect the simulation. Okay, so let's focus on the structure. So the structure are these columns here, these beams here, and then the supports. And the supports are exactly identical to the previous one. So we have this fixed support at the very base, these 4 points here. And then all the upper points, they are blocking rotation, but they allow translation of the joint. Okay, so in terms of supports, it's perfectly identical to the previous one. We only have more levels, more stories in our building. And the main thing here is the definition of the geometrical aspect of the cross sections, both of columns and beams. So you see this pink component here. This is a very important component when you perform some optimization process. It's called the gene pool. Actually, the gene pool is something that you find next to Galapagos, because basically, even if Galapagos allows optimizing only just one fitness value, just one number, this number can depend on a huge amount of parameters, or in general, or more than one parameters. Okay, so that's why the gene pool exists, and this is the Grasshopper component. Okay, so we are not the opossum plugin and the goldfish plugin, they only contain the solver, the optimization solver. Okay, the gene pool is something that you have in your Grasshopper installation. So the gene pool is actually a set of sliders with a defined range and a defined amount of sliders. So with this, for example, you see that in this case, if I double click on this gene pool, I have 16 genes, which means 16 sliders. They all have 2 decimal numbers, and they all share the same range between 0.25 and 0.50. And this is affecting actually the width and depth of the cross section of our columns. And also, it's affecting probably, it should affect, yeah, it's affecting also the height, the width of the beams. Okay, so we have the beams sitting perfectly on top of each column, okay, with the same width. And then there is this other slider here, which is once again 16 sliders with 2 decimal numbers between 25 and 50, which is defining actually the height of the beam. You see that these are connected also to other things. This is because I was tagging with some labels the beams and the columns, but also they converge inside this expression. So this expression is actually calculating the beam mass, because I am applying this, I'm using this as a linear load applied to the columns. Okay, so in this case, I multiply the x, y, and z, which are width, depth, and height, or length, for example, of the beam body, by the weight of concrete, well, the average weight of concrete. I'm not considering, in this case, the iron bar or reinforcement bars and so on. Okay, this is an ideal thing that I did here, but you can be as precise as you want, of course. Normally, you might want to use some percentage in order to come up with an average weight of a reinforced concrete beam. So normally I would not recommend to be too much analytical in this phase. Okay, so the beam mass is this value, and this is actually inverting this this value here. So it's going to be applied in vertical and negative direction, and it's going to be used like a linear load. So it's not a generic linear load. It's the linear load that the columns are receiving depends on the weight, the width, the height, and the material of the beams. Of course, this value here, 2549, is not connected parametrically to the material. So if you change the material here, like for example to rubber, well, it sounds stupid, but if you change this to rubber, you must put here the weight relative to rubber, okay? But you must do this manually, okay? Like going inside this this expression and changing this value manually. This is not happening automatically. If you want, if you want to create a template definition, you might want to use, I don't know, something like a value list. And you can define this value list like, I don't know, concrete, and then you place here the weight, and then you define here, let me play funky. So rubber, let's say it's, I don't know, 50. And so when you name this value list like material, so when you change this from concrete to rubber, you will have the corresponding weight coming out from this. So you don't have to manually edit your expression, because you can add another input here and plug this to the additional input that you create, and then substitute this number with the fourth variable that you create here. So once you change this, you also change this accordingly, like with this menu. Okay, so you can make it easier than manual editing this value here with a value list. But anyway, you can also do a totally automatic definition if you want, just to give you some ideas. Okay, because I think it's important also to um, come up with some strategies. Okay, so for example, if I copy this material here, I can also create a copy where I have this set to rubber. Okay, so these are the two materials that I want to take into account as for my structure. Okay, so concrete and rubber. Um, so what you can do here, this is actually not the choice of the material. This is actually the material weight. Okay, this is defining the material weight by material, concrete and rubber. So let's say that that you want to decide with just one selection both the material and change the weight inside the expression. Okay, in that case, I would use a stream filter. Okay, so this is a Grasshopper component that allows somehow a conditional statement. So for example, let's say that I create another value list. Well, actually, the real value list that we need here is going to be actually the material. And here I want to define concrete like 0 and rubber like 1. Okay, so what's happening with this stream filter is that you plug here all the streams that you want to use. In our case, it's going to be the weight and the material, and then you decide which stream you want to consider. So if I select concrete, it's going to be the stream 0 that is going to come up from the stream filter. So for example, if I have the weight of concrete, which is 2,500, and I have the weight of rubber, which is 50. I'm inventing, right? So don't think these are exact values. But anyway, so stream 0 is going to be basically the material concrete and the weight of concrete. You can do, depending on how used you are with data manipulation, you can plug the material and the weight to stream 0 and rubber with its weight to stream 1. So if you do this, as a result here, you will have two values coming out, which are the material and its weight. And you can separate them and use them inside your definition accordingly. And when you want to switch to rubber, you just select rubber, and here you have rubber with its weight. And everything is going to be sent to the proper location inside your definition. So this is like a switch where you can change material, and everything inside the definition will change accordingly, both the material for the cross-section definition and the weight for the load calculation. Okay, so I will leave it like here, so you will have it like a reference. But I do invite you to create this kind of automatic workflow in your definition, because this allows to work less. So I will leave it like this. Let me say from time to time, because I'm going to share this definition with you at the end. So I want these changes also to be maintained. So let's go back to this gene pool. So the gene pool is actually a very stupid component. It starts with 10 sliders, 2 decimal number between 0 and 100 as a range. Okay, you can customize it totally. Now, the bad thing about gene pool is that it's not parametrically connected to anything. Okay, so for example, if we have, if we must define, for example, the cross section for all the columns of our building, we must manually or somehow, let's say, ask Grasshopper to tell us how many columns we have here, and there are 16. And then we can double click here and manually edit the amount of genes, the amount of sliders. Okay, so this is something that you must do manually. There is no way of determining the amount of sliders inside the gene pool automatically according to something that's happening in another part of your definition. Unfortunately, I would say. And the same happens here with the beams. So for each story of the building, we have 4 columns and 4 beams. So it's simple to understand that we have 16 beams and 16 columns. Okay, so we have 2 gene pools. Each one contains 16 parameters, let's say so. And of course, each one of these parameters is affecting one cross section. Okay, so you see that in this case, the grafting, it makes more sense because we grafted the start point and end point in order to separate the start and end point of each frame element. And now we are grafting also the cross sections because these are 16 different cross sections, okay, for the columns, and 16 different cross sections for the beams. And we want them to correspond one to each of the frame element. So we graph them all together. The load, for example, is not being grafted because it is applied as one single load value to all the elements, to all the beams of our structure. Of course, if you want to apply a different load to each of the beams, you would have to graft the loads as well and provide one load for each beam. Okay, so this is just data manipulation. It's not the behavior of the plugin. Okay, but this is something that I always repeat. Data manipulation is the key to make everything work, whatever plugin you are using. Okay, so it's way more important to learn data manipulation than learn the usage of one specific plugin. So here is basically that's the reason why we have this grafted cross section, because actually we are working with several cross sections, one per each structural element, frame element. As for the rest, it's absolutely identical. You see that we have the material, we have the cross section. In this case, I have taken square solid, and here at the bottom, I have taken the rectangle solid. Okay, so this is basically the only relevant news in this definition is the gene pool usage. Now, we define the frame element. You see that they are defined separately. There is one frame element per branch in this data tree. This is the effect of having our grafted data. So you see that also the beams are, the rectangle solid beams are separated by branch. But anyway, it doesn't matter because when you plug these all these elements here, you simply flatten the input. You see that these components have another characteristic, which is they don't show the data manipulation switches in the input and output. So even if the model components here is flattened, you see that it's activated, the flattening option. You don't see the arrow pointing down here at the component level. So this is something that it's like weird, but pay attention to this because this is something that you must do, because model components must be provided as list, as the component is saying. Because if you don't provide them as a list, they don't blend into one single FEA system. Okay, so pay attention to this. Eventually, if you want to have a, let's say, error-proof definition, you might want to create a flattened tree component and always place it here, like connect everything here to the tree input. This is going to flatten everything, and you plug this into the model components. Okay, so if you want to have a more clear understanding of what's going on, you can do this and avoid any misunderstanding. And so there is the FEA system, the FE solver, and now you see that in this case I am concentrating on both max deflection and weight. Besides the system physical, or let's say aesthetical representation here with the frame visualization with deflection, or whatever you might want to use, I am concentrating on these two outputs, max deflection and weight. So what I'm going to do next is going to use Goldfish in order to optimize our structure according to the maximum deflection and the weight of the structure. Okay, so this is the next step.